Hello, welcome to Into the Fire, a Burning Coal Theater Company podcast series.
Hi, this is Jerome Davis. I'm the artistic director of Burning Coal Theater Company, and I'd like to welcome everyone to Into the Fire, the Burning Coal Theater Company podcast series on all things theatrical. Today, we are going to have a special presentation joining the cast of Copenhagen, the play that Burning Coal will open its 28th season with on October 10th, will be Marc Kastner. Marc was the head of physics at MIT. He later became the dean of science at MIT, and after that was appointed by President Barack Obama as the undersecretary for the Department of Energy. And he is now a professor emeritus at MIT and doing research work at Stanford University. This conversation will be joined in progress. Enjoy it.
So continuing along those lines a little bit, do you have a sense? I mean, I want to ask about some of the actual science of this, and I know that all of our actors have questions that they want to ask you. But one other question I had is: do you think that Heisenberg knew what he was doing in not doing the math as the play describes, or do you think it was divine kismet or lucky strike, as the play talks about?
Well, I think it's impossible to know. Certainly, when the German scientists were captured by the British and held in this, what was it called?
Farm hall, the farm
hall, right? They had wiretaps, so they listened to everything they said. And when the announcement was made of the bomb being dropped at Hiroshima, they were all in a state of shock. So it's hard to believe that they really thought it could be done. But it's easy to make these mistakes. When Fermi built the first nuclear reactor under the football stadium in Chicago, he had done really detailed calculations which predicted that the reactor could be made to go critical. That means you get enough fission reactions to make enough neutrons to start amplifying things. And of course, if you don't control it, it gets very hot and melts down and causes terrible disaster. So he was pretty confident because he trusted his calculations, but nobody was completely sure. And apparently he thought that they would need a huge amount of enriched uranium. Let me step back a second. The uranium used in the first reactor was just just uranium that was mined and chemically purified. But the isotopes in uranium, the atoms of uranium have different isotopes, which are atoms with the same number of electrons and protons, but different numbers of neutrons in their nucleus. When he tried to calculate how much of that uranium you would need to make a bomb, it was a gigantic amount. And there was a story I heard when I was at Chicago that when he first talked about the Manhattan Project with some generals, they asked, what would I need to deliver this weapon? And he said, I don't know, you might need a freight car. And so they said they weren't interested, right? And so there was so much unknown that it wouldn't surprise me at all if they really didn't, were not able to figure out how to do it, if Heisenberg were unable to figure out how to do it. They made a strategic mistake in that they tried to use heavy water to moderate the reaction. I think this is mentioned in the play at some point. Heavy water is H2O, 2 hydrogen atoms and 1 oxygen atom, but you can make hydrogen with an extra neutron, and then we call it a deuterium atom. And heavy water is water in which some of the hydrogen is replaced by deuterium. And it's an excellent way of slowing down neutrons. When you want to make a reactor, you don't want the neutrons to move too fast because they get captured by other uranium atoms more easily if they're moving slowly. And so you need a moderator to slow them down. And Fermi figured out that pure graphite was the best kind of moderator. But Heisenberg correctly realized that deuterium would be a great moderator. The trouble is, it's very hard to make deuterium. And I think there was a big facility in Norway somewhere trying to make D2O, heavy water, but they just weren't making enough of it to make a reactor.
Or come to that conclusion?
I don't know exactly. I think throughout the war, they were trying to make the D2O, and I think there was a big effort on the part of the Allies to sabotage that facility.
Interesting. Well, I've talked a lot. Do our actors or others in the room? Ian, you have a question?
Give me twice to finish my notes.
Okay.
I hadn't thought of that at all about the heavy water.
Yeah. Anybody else, Brian or Linda? Any questions?
No, I'm just being educated. I just want to.
I have plenty. Well, are you ready?
Yeah,
Go
if I
for
could. So
Take it away.
one of the things, so Heisenberg sort of has 2 major discoveries which are discussed in the play. One of them is uncertainty, but the other one is when he's at Heligoland and the matrix calculations. And I believe this is what is referred to when they say that Heisenberg and Bohr invented quantum mechanics. What I don't understand is exactly what those matrix calculations sort of revealed. Like what was the practical outgrowth of this discovery that's there?
So let me step back a second and give some more of the history. In my view, and people will give you different views of what's most important, different historians of physics. But in my view, you really have to think about quantum mechanics as being an outgrowth of the Industrial Revolution in some ways. During the 1800s, because people were making new machines all the time, there were new kinds of instruments being built where you could measure things you could never measure before. Even Faraday, measuring electricity and magnetism, really opened up a completely new world, and Maxwell was the theorist who put all of that together at the end of the 1800s. But one of the things that was happening was that people were able to measure spectroscopy in ways they couldn't before, which means breaking up light into its different colors. And for the first time, they saw that if they looked at a lamp made with a discharge of sodium, for example, they would see very sharp lines. And there was just no way of understanding this with classical physics. So there were a bunch of observations that sort of forced people to start thinking about things in new ways. And Bohr was the first one who came up with the idea of quantization, which means that if you think about an atom, then the electron orbits around the nucleus, but it's not allowed to be at any distance from the nucleus. There are only specific distances which are allowed. And that's what came out of the Bohr model of the atom. So in some ways, Bohr was the first person who came up with a picture of physics which involved quantization. The quantization of the orbits led to a quantization of the energies. But what Bohr did was actually very simple. Once you understand the Bohr model, any undergraduate can work it out in great detail. There's really nothing to it. But then a bunch of people, and especially Heisenberg and Schrödinger, really started to try to quantify this in more general ways. And Schrödinger took an approach where he described the particles as waves. And he understood that there was this complication that sometimes a particle behaved like a particle and sometimes it behaved like a wave. But that was very hard to quantify within the wave picture that he developed. And Heisenberg's matrix picture made it much clearer. So it was really this matrix approach that in some ways led to the uncertainty principle, because you could write down a certain equation involving the matrices that would give you the uncertainty principle right away.
Brian, you had a question.
I have two, actually. Early in the play, Heisenberg says about me that Bohr was the first one to realize that quanta applied to matter as well as to energy. So when you talk about quanta applying to matter, you're talking about the orbits being discrete, the electron orbits being discrete distances from the nucleus, correct?
Correct.
And can you tell me that, thank you, and can you tell me that prior to my understanding of that, what does it mean when he says that I understood that I explained that quanta applied to matter as well as to energy. How did it already apply to energy? What's the understanding of that?
So the history is that the idea of the quantum was first discovered and understood in terms of light, of electromagnetic energy.
Yeah.
So it starts with Max Planck, who was studying the radiation from hot objects. We call it black body radiation because it's perfect when the material is completely black. But it's the radiation given off by things that are hot. So when you look inside your toaster, you see the metal glowing red. That's black. That's basically Planck radiation. And he needed to invoke the quantum for light in order to explain the spectrum of that radiation. And then the killer was Einstein's interpretation of the photoelectric effect. So when you shine light on metals in a vacuum, you see electrons coming out. And the energy that those electrons have depend on the wavelength or the color of the light. And that you can only understand in terms of quantum. And in fact, Einstein won the Nobel Prize for that paper, even though in the same year he had published his theory of relativity. But so few people believed it that they gave him the Nobel Prize for this one. But so by the time Bohr started thinking about the spectrum that comes out of atoms, individual atoms, which you see when you have a gas discharge, like in a sodium lamp on the street, the idea that the light was quantized was already established. But the idea that the atom's energies were quantized had not been established. Does that answer your question?
Brian went to MIT too, Mark, by the way. He was in the chemistry.
No, I graduated in electrical engineering. I don't know when you were there. We might have been there at the same time. I haven't exactly.
I'm sure we were.
Yeah, he's not been practicing, he said recently, but
Complained about science.
we've well cast for this one, Mark. So the two big sort of most known scientific ideas, or people think they know them, I guess, are the theory of relativity and the principle involving Schrodinger's cat in the box. Can you describe those just maybe just in layman's terms, like what the practical, what they are? Yes, exactly. Simple language so that Margareta can understand, and there she is, and also so I can understand. And but what are they exactly, and what good does it do to know it or to have these principles? So.
Well, so the theory of relativity, which Einstein came up with in 1905, includes lots of predictions about the way things behave when they're moving close to the speed of light. It's based on the idea which Einstein assumed, that nothing can move faster than the speed of light. And if nothing can move faster than the speed of light, then you start to ask, what do things look like if you were moving close to the speed of light? And you get all these weird answers. And the most interesting one is that the mass of an object starts to get heavier if you accelerate it close to the speed of light. And the mass is given by E equals mc squared, where E is the energy and the mass is m, and then c squared is the speed of light squared. So objects get heavier if they move faster, and if you have them at rest, they still have a mass, which gives an energy, which is E equal mc squared. So this is important in fission, because when a uranium atom breaks apart, so a neutron gets captured by a uranium atom and it breaks up into two other pieces, the weight, the mass of those two pieces is not the same as the mass of the original nucleus. It's a little bit less. And that difference is the energy that goes into, that is released, either in a reactor or in a bomb. So the relativity is absolutely crucial in understanding both of those things in nuclear physics. So you asked me about relativity, and the second was?
Schrodinger's cat.
Schrodinger's cat. So this is a really complicated thing. And there are still people who argue about the reality of this. The Copenhagen picture, which the Copenhagen picture of quantum mechanics came from Bohr and Heisenberg and everybody working with them. And their picture is that you can describe any particle as Schrodinger did as a wave if it's moving. And if it's moving and you don't interfere with it, it'll just behave like a wave. So for example, if you make two paths that it can go through, and they talk about the two-slit experiment in the play, if you imagine sending electrons towards a wall with two little holes in it, then on the other side of the wall, you get a pattern which looks like the pattern you would get if you shine light on those two slits. That you get an interference pattern because you can't know which slit the electron went through. It's a wave, and the wave extends over the distance between the two slits. And so you just can't know where the electron went. But if you took a little light and shined it on one of the slits so that it would bump the electrons every once in a while, kick them out of the direction, then you destroy the pattern completely. So the Copenhagen picture is that a measurement interferes with the system. It changes the system. And the uncertainty principle is that if you, with this light source, if you can pinpoint where the electron was going, then you've made its velocity completely uncertain. So it can be going very fast, and that's why it destroys the interference pattern. So Schrodinger's cat is an idea that it's a picture that Schrodinger came up with because he didn't really quite believe, he didn't believe this Copenhagen picture. He thought this just wasn't right. And Einstein didn't believe it either. It's when he made the famous statement that God doesn't play dice with the universe, right? Because this is a very probabilistic picture. You have some probability of the electron going through the left slit and a probability of going through the right slit, but you can't tell exactly where it went. And if you try, then you destroy the experiment. So Schrodinger said, well, let's apply this to a more human size experiment and think about a cat in a box with a vial of cyanide, which gets opened if a nucleus decays and hits a Geiger counter. And then you start to get into this philosophical question of whether it's the knowledge of the observer that matters. It doesn't matter that I don't know what's going on inside the box. The Copenhagen interpretation would say it doesn't matter, and that once the Geiger counter it clicks, once it detects the decay of the particle, that has destroyed the experiment and put it into one state or another. And so it doesn't matter that I don't know. It was that there's some macroscopic interference with the experiment, and that interference is done by the Geiger counter. But this is still, as I said, I think there are people who still argue about this.
The skiing metaphor apply there. Go left or go right, and you survive. But if you don't make it, have I got that right? If you don't make a choice, you die. Is that another version of the same idea?
Yeah, exactly.
Brian?
Right, I've got two. I remember the second one I was going to ask last time. So I'll go that one first. So Bohr came up with this idea of what the Bohr atom, what it looks like. What did the atom look like before? What was the working draft of what the atom, and who came up with that? Was that Planck?
So you're asking, what did people think the atom was before Bohr?
Yeah.
So there was a model from J.J. Thomson. J.J. Thomson discovered the electron, not that many years before. You gotta understand, all of this was happening at lightning speed. There's Einstein discovers relativity, then Thomson discovers the electron, and then Rutherford discovers the nucleus. All of this is happening in the space of 20 years or something. So Thomson knew that the atom had electrons in it, but he didn't know about the nucleus yet. And so he had a model in which the electrons were moving or they were stuck like raisins in a bran muffin, and the bran muffin was the positive charge, and the electrons were just stuck inside. I think they call it the positive charge jellium, right? You know, they really didn't know, and it was very hard to find experiments that would test it. And then they started seeing these lines, and that's when everybody said there's something else going on.
So a lot of this was let's see if this works, right? It wasn't necessarily this is, you know, I've staked my reputation on this. Is that right?
I think there's a lot to that, you know. So physics tends to glorify the theorists, right? But there are very few cases where the theorists have invented something from nothing. The only case I know of is Einstein's relativity, which he generated without any experimental evidence, as far as we know, just from thinking through what he thought had to be the case if nothing traveled faster than the speed of light. But there's no question that people like Bohr and Heisenberg and Schrödinger were being guided tremendously by the experimental measurements which were going on at the time. Much of it on the hydrogen atom. So the hydrogen atom is the simplest atom. By that time, they knew it had to have, you know, the smallest nuclear charge and only one electron. And so it's the simplest thing you could have, and that's the thing they were trying to model.
Ryan, you had two questions.
I did. I want to ask you about complementarity. If you can sound
Complementarity.
sound like that for me, or not, or talk for 20 minutes.
No. It's really it's very important. I'm trying to, you know, I wrote down some notes. Let me open the script again and see. Do you remember where it is?
I kind of remember what I say about it is that if you look at a particle, if you look at something, whatever it is, you can either look at it as a wave or as a particle. But
Okay.
but when you look at it as a particle, there are some things you can't know about it. And if you look at it as a wave, there are different things that you can't know about.
Right. So that's exactly what it is. It's the fact that a particle can be either a wave or a particle. It can look like a wave or a particle, and it depends on how it's prepared. So if you make a beam of electrons, which, you know, is what's inside an X-ray machine, for example, as long as it's a beam, you don't know where the electrons are in the beam, and so it behaves purely like a wave. But as soon as you hit that beam with something else, for example, with light, with other X-rays, and the electron scatters, then you can trace where the electron scattered from, and you know exactly where it was at one instant of time. But then you've made it, you've lost all information about its velocity. So complementarity is connected with the uncertainty principle. It's really the uncertainty principle again.
Wait, it is the uncertainty principle? It's related to the uncertainty principle.
It's related to, or it is Brian's question.
Well, it's related to it, because the uncertainty principle is broader and involves other quantities besides position and velocity. And at least in my mind, complementarity only involves position and velocity. But so, for example, there's an uncertainty principle between energy and time. And that shows up because if if an atom is in excited state and it drops down by emitting a photon, then there'll be a spectrum of light that comes out, which is not exactly quantized. It has a little spread, a tiny spread. And that spread is given by how long the atom lives in the excited state.
And that's
So
what you see on a spectrograph?
Pardon?
And that's something you'd see like on a spectrograph?
Exactly.
Yeah.
Exactly right. So there are actually a huge number of uncertainty principles with different variables. And so I think the uncertainty principle is in some sense broader than complementarity.
I asked a question yesterday that was met with stony silence from my comrades, as is often the case with my questions. So I wanted to throw that out there to you, Mark. So part of what I understand that to say is, if you know the speed of something, you can't know the location. And if you know the location, you can't know the speed. Does that mean that those two things are unknowable? I mean, the truth of those moments are not, don't exist.
No, it doesn't mean that. It means there's limits to what you can know.
To what a human mind
So you can limit the position over a finite range, and that will make the velocity uncertain over a finite range of velocities. Right? That it says that there's a connection between how well you know the position and how well you know the velocity. If you know the position perfectly, then the velocity is completely uncertain. If you know the velocity perfectly, the position is completely uncertain. But in between, you can have any trade-off you want.
But if you know something's position, absolutely, you cannot know its velocity, but that doesn't mean it doesn't have an absolute velocity, correct?
No, on the contrary, it means its velocity probably is infinite.
This is yeah. That's really what I was getting at. Is there I can't even articulate it, but is there a speed at which it is going? We just don't know that speed. And it sounds like you're saying it's going at every speed.
It's just the speed is just completely uncertain. You really just have no knowledge of it. But it's certainly true that if I made a box and put an electron in it and started to make the walls tighter and tighter, so I'm confining the electrons to a smaller and smaller space, then it starts rattling back and forth faster and faster and faster. And if I shrunk the walls to zero, it would be going infinitely fast back and forth. Of course, it can't go faster than the speed of light, but this is not a realistic experiment anyway.
I wanted to ask a couple of questions that are just about the drama, inherent in the play. One of the things we see in the play is Margaret is the spouse, who is one of my favorite characters in all of drama, because she listens so well, and she's, this sounds patronizing, but she's trying very hard to stay with these guys, and she's smarter than they think. Well,
she's smarter in ways that they will never be smart.
Is that an accurate depiction of families, of people who have this level of capability and knowledge?
I don't think you can say it's typical. We know of Schrodinger had notoriously terrible relations with women, and had many relationships with women, and none of them were I don't think any of them paid attention to what he was saying, probably. So I think this is probably unique. I think Bohr, you know, of course, each of these personalities is very, very unique. You know, I know some very famous scientists whose wives worked very hard to understand what they were doing, and others have no interest.
Does it alter the relationship one way or the other, or are both equally solid?
I don't know. I think most of the people I think of, their spouses really, you know, don't want to get into the details.
And then the other thing that interests me very much about the play is the joy of the clear joy of the two men's friendship. Is that accurate? You know, do you feel there are moments in the play where you feel like it's two 12-year-olds talking about baseball for the first time or something like that? There's just such joy and excitement in learning and sharing with each other and learning from each other. Is that an accurate thing, or is it a more singular sort of solo experience mostly?
Well, again, there's a big spectrum, right? So I think, you know, Einstein was very much did things very much on his own. But there's no question that the people around Bohr were very collaborative. And, you know, I myself have had some really, have had a variety of different collaborations, but the very best ones are where the participants really feed on each other's ideas. And you know, there's no question that's what was going on around Bohr. I think that's what made him so special, that he really he brought out the best of the people who worked around him.
His wife makes the point in the play that his memory is faulty and that none of these things happen together but singularly. Do you think Michael Frayn is trying to make a point there, or is that just an historically accurate?
So I don't know the answer to that. You know, I think that's very interesting. You know, in my own experience, even when I've worked extremely closely with a very strong collaborator, you know, there were times when we were kicking things around and then we would go off and we'd have ideas on our own and then come back. So I wouldn't be surprised if a lot of that happened.
Walking is a big motif in the play too. Is that something you've experienced in your life?
Not. I haven't. I think it's more typical of theorists, because, you know, when they're working, if they're just sitting or writing, it gets pretty stale, right? So I think, you know, the story of theorists walking and figuring things out. Fermi was really famous for his walks. Apparently, he would walk, you know, through the hills, and if he saw a power line, he would immediately start making measurements by eye and calculating the shape of the curve, you know. But his walks were famous, so I think that's really quite typical of the theorists.
Mark is a tennis guy, so that's how he stays fit. He's a very good tennis player. Any other questions?
Yeah.
Yes.
So circling back to the start of our conversation, talking with you has made me realize the degree to which the bomb, right, has sort of been this shadow over physics, you know, for that period, obviously. But I wonder to what degree, even now, that knowledge that this discipline, which is about revealing the actual truth of the workings of the universe, also has revealed one of the worst things that we could do as a human race, right? To what degree does that still overwhelm or affect the discipline now?
I would say not very much. The generation that worked on the Manhattan Project is gone. Nuclear physics is no longer considered a forefront field. So MIT is one of the few places that has any people working on nuclear physics. And the kinds of things they do is so far from fission or fusion that I don't think they feel any connection with the nuclear weapons. Although I think it is true that the government still supports nuclear physics because they need people to go to the weapons labs and maintain the weapons so that they don't deteriorate, right? But I don't think it hangs over the physics community anymore. One thing I did want to mention, which might be interesting to you, is that I was thinking a lot about Heisenberg in this context, and he's a very controversial figure because he worked for Hitler, right? But he was such a hero to the scientific community that I remember when he came to the United States, people like Weisskopf were so anxious to see him and talk to him, even though Weisskopf was a refugee from Nazi Germany. He was a hero because of what he had contributed to physics. And the fact that he worked for the Nazis didn't change that for everybody. I'm sure for many people it did.
Well, I love him so much because he's such an insane contradiction, right? He's right out of Shakespeare. It's fantastic.
Is there anything you had wanted to say about the play, Marc, when you read it for us, last week, I guess, or 2 weeks ago? Is there anything that struck you about it that you feel is important to think about or know about?
I think we've touched on most of the important things. There were a lot of details, and there are amazing number of details. For example, Heisenberg complaining that he doesn't have a cyclotron. And that seemed to me a little peculiar because that's something an experimenter would work on, not a theorist. But of course, if he was running the entire nuclear program for the Nazis, then he would want a cyclotron. The cyclotrons in the United States were way ahead because Lawrence, who was at Berkeley, built the first cyclotron and built many others. But I didn't quite understand why the playwright emphasized that. It seemed strange to me, but.
And a cyclotron is used to separate.
So it's used to separate isotopes, but more important, it's used to accelerate particles. And so all of the atom smashers that we know about, right, the particle accelerators, now the biggest one in the world is at CERN in Switzerland, and it has, 10-mile diameter or something. And the highest energies we can achieve on Earth are in these cyclotrons.
And is that, you said that atomic research is no longer sort of the cutting edge of physics research.
Nuclear physics.
Sorry, yes, nuclear. Would you say that like what's being done at CERN and those sort of things represents that leading edge?
In one part of the leading edge. The leading edge has become more diverse. So there, astrophysics is another area which uses nuclear physics and particle physics. This creation of quantum mechanics just changed everything. It changed how we think about the universe, and it changed how we think about materials. It's the reason we have lasers and computers. All of our daily lives now are based on quantum mechanics. When you think about it, it wasn't that long ago that it was invented. It's pretty amazing.
Will there be another moment like that?
No.
Okay.
Well, so the other thing to say, which is really important, is that as physicists, we are always trying to find things that are universally true. And universally means really universally. It means that when we do observations of a distant galaxy, thousands of light years away, that the rules are the same there as they are here. And quantum mechanics was a discovery of a huge number of universal principles that are applicable everywhere. There's no other field where there is such universality. In biology, we have Darwin, we have evolution, but we don't know that it happens the same way on other planets, right? It could be entirely different. The thing we know on other planets that's the same are all the laws of physics.
Well, that's all fantastic, Mark. Thank you very much. That's helpful. Any last comments before we?
Oh, that was great.
Thank you.
Thank you. This has been really fun for me.
Say hello to Marcia and Sonia and everybody. And we will see you soon.
Good. Thanks.
Take care.